Alright, hello everybody and welcome back to Environmental Science. So here we talk about fire, which is cool. Okay, also important. So what are we trying to do? We will look at the basic physics and chemistry behind fire, fundamental stuff. We'll talk about the development of fire in human history, where it came from, what it was used for, why it's important. We will put fire in its place, ecologically speaking. Also, not really. We'll talk about how views of fire and nature have changed over time, talk about some important ideas behind that. And then finally, we will look at fire as a hazard, including case studies, including wildfire, and including fire in the state of Arizona. So let's do it. We got 4 sections on this one, all right? Fire basics, fire and ecology, fire hazards, fire in Arizona. Cool, so let's get started. So the first thing, I will try not to get too poetic with this, right? But you kind of have to. So fire is going to be a really helpful concept to keep in mind, right? So some things get better when you stress them out. Some things get worse when you stress them out, as captured by our little metaphor here, right? Wind extinguishes a candle, but energizes fire, right? Stress makes some things better and other things worse. Good to know. So what exactly is fire? And you can maybe pause the video here and try to come up with an explanation on your own if you don't feel like you have one. Okay, so we've got the chemical reaction for it for combustion, which is going to be our scientific word for fire, right? Fire is a chemical reaction, right? You can think of it as like a chemical chain reaction. You can think of it as being an avalanche that keeps going until something stops it. Would be a good way to think about it in your mind. It takes in what? Fuel, oxygen, and some sort of spark, and it puts out carbon dioxide, water vapor, energy, and combustion products, right? So this reaction over here is not a perfect process. This is kind of an idealized version, which is why it's not terribly important for us to learn it. We have some sort of fuel, so this is methane, it's a hydrocarbon, smells bad. We have oxygen, which is available in the air, right? We ignite it with a spark, and what do we get as the reaction proceeds? We get a release of energy, we get CO2, carbon dioxide, gas going up into the air, and we get H2O, water in gaseous form, right? So you need 3 things to get a fire: oxygen, a fuel source, something like wood, could be methane or anything else, and you need a spark, and then it releases 4 things, right? So water vapor, carbon dioxide, energy, and combustion products, which is going to be this broad term that includes everything from carbon monoxide to particle pollution, all the other things that happen because this process is not perfect, right? We get incomplete combustion. The fire triangle is a good way to remember this, and a really good framework for thinking about it, right? Fire needs 3 things, generally speaking, right? When we talk about how to manage fires later on, how to put them out, it's by denying fire one of these 3 things. You gotta have oxygen, you gotta have heat or a source of ignition, you gotta have fuel. So it could be wood, it could be dead plants, right? Or it could be some sort of human-made source like gasoline. Now, we talked about Earth's atmosphere. Maybe pause your video and try to remember what percentage of Earth's atmosphere is oxygen, roughly. Okay, so it's going to be about 20%, right? So 80% of it, roughly speaking, is this nitrogen gas, which is really important, cycles through living organisms and the environment, but doesn't really react with stuff. The nitrogen molecules are bonded to each other really strongly, and they're just not interested in you or what you're doing, so stop. 20% of it, though, that is oxygen, is extremely reactive, right? So we talked about how different elements on the periodic table essentially had different personalities. Oxygen's personality is that it gets into fights with everything, really. The fact that we have free oxygen in our atmosphere is unusual because in basically every other setting you can imagine, we don't have plants, right, or life like on other planets, right? You don't get free oxygen in the atmosphere, right? Because it's so reactive that it, chemically speaking, just starts a fight with everything and makes all these other, products, and then it's gone, right? Free oxygen is also one of those things that if you were to find it on another planet, let me know, because that means there's something there. Awesome. So, not super critical content, but we've talked some about the history of the Earth, and we can talk about now the history of oxygen on Earth. So, billions of years ago, we have the first photosynthesizers deep under the sea, pumping out oxygen, little blue-green algae that's doing its best. Typically, shallow, warm waters, tropical, awesome. Puts out oxygen. A lot of it at first is actually absorbed by the ocean, reacts with a lot of stuff in there, and takes a lot of junk out of the ocean, which is good. But then eventually, as they keep producing oxygen, it fills up the atmosphere and coincidentally kills like 99.9% of all the other life that was on Earth at the time. Why? Because oxygen is really reactive. It reacts with everything. The norm is that oxygen, like, kills stuff or reacts it out of existence, reacts it into a different form, all right? There's only really been enough oxygen in the atmosphere for fire starting about 400 million years ago. So we can look at our timeline. If I can find my cursor, there we go. So right here is about 400 million years. This is about 10% of the way back in Earth's history. We will notice, right, oxygen peaks shortly afterward. There are big dragonflies here absorbing oxygen through their exoskeleton, their skin, bigger than anything that can be supported these days. It has a massive drop-off right about here. And you might recall that there was this thing called a mass extinction that occurs right about 250 million years ago. Not a coincidence. There's a big anoxic event, right? Moving forward, right, we have another oxygen peak, and then it comes down to where we are today. And that drop-off at about 60 to 100 million years corresponds with another mass extinction, but is not as important for that one, right? So, oxygen hasn't always been there. Important context. Thermal conductivity is going to be one of our important concepts, right? So, you can imagine, right? You take your hand and you stick it inside of an oven mitt. Does it feel hot? Do you want to, like, yank your hand out and, like, yell? No. Okay, what if you take your hand and you put it against a really hot seatbelt buckle that's been sitting in the sun in a hot day in Phoenix? Okay, right. So what's different about those two things, those two different materials, right? One made of metal, one made of a cloth, is that the one made of metal has a really, really high thermal conductivity. So we hear this word, maybe you think of electrical conductivity or conducting electricity, right? And it's kind of the same idea, right? If something conducts electricity, it means it moves it really well from one place to another. And this is similar, right? So if something has good thermal conductivity, really high thermal conductivity, it means that it moves heat really well from one place to another. Like what? Like metal, right? Like your seatbelt buckle. So conduction, right, is going to be the process here. We're not super concerned about like different methods of heat transfer, right? But conduction means you're touching the thing to get heat from it, right? Like touching the hot stove, as opposed to other forms where heat's transferred indirectly. Units here, I have the technical units down below, watts per meter per Kelvin, right, if you wanted to be official. But the way that makes sense to me, I think of it as being energy flow per meter per degree, which is equivalent, right? But if we look at our example, right? So we have a fire, right? Energy source putting out lots of heat, right? We have our person who is sensing the heat coming through the floor here, right? Now, how much heat is going to be delivered to this person's hand? Well, it depends. Depends on what? The energy flow, right? Depends on how many meters we are away, and it depends on how many degrees difference we have. Essentially all it comes down to. I've got some common values for this down here. We notice metal extremely high. Water, well, looks low, but is actually much higher than something like air, right? So we might imagine being in a kitchen, right? You have like a clean white towel. You use it to pick something up and move it, right? Totally fine. But if somebody else was in there and spilled water all over that towel and it's like wet and you try to do that, not good. If you don't believe me, try it out. Well, maybe don't. Just believe me. Okay, this is separate from, right? Separate from heat capacity, right? Which is looking at the amount of heat you have to put into something to bring its temperature up, right? These are not related. These are separate concepts, and it's important that we keep them separate in our minds, right? So this is the amount of energy that it takes to raise the temperature of something. Units for this one are energy per degree or energy per degree of temperature that you're raising it per gram of stuff that you have. And that second case is sometimes called the specific heat capacity. We're not interested in that one, but we are interested in making sure heat capacity is different from conductivity. This one is how much heat something can hold on to, whereas conductivity is how much heat we transfer, right? How quickly we transfer heat from one place to another. Awesome. We have run into this a couple times, right? We talked about how soil and the ground generally will hold on to its heat a lot better than air does, and as a result, soil temperatures tend to be higher than air temperatures, broadly speaking, though this evens out somewhat with depth, right? And we've also talked about climate change and how the atmosphere really doesn't hold as much heat as the oceans. Oceans hold far more, and because of this, they're going to continue to hold on to that heat and release it for years to come, even if there are changes in the atmosphere. Fire comes in different types. Last thing that we're going to talk about here, right? So there are many fire types. This is really not critical stuff, but fire extinguishers, right, like any fire extinguisher that you get, is going to be rated for different types of fires. So this could come up. So type A fires are the most common type that you probably think of in your head, right? Burning wood, paper, building materials, things of that sort. Type B fires are going to be like liquid fuels and fumes. You know, if you have a gasoline fire. Type C is going to be electrical equipment. So I don't know if you have a server room somewhere or like a warehouse, well, more of a server room. Warehouse. Type D is going to be metal fires, which is specific. And then there's a special category, they call them type K fires, for grease fires in a kitchen. Now, most fire extinguishers that you run into are going to be dry powder. I don't specifically know the ones that we have at the school, but this is the vast majority of all of them, which is pretty good against pretty much all the different types. Other more specialized kinds might be found in a laboratory, might be found in an industrial setting for those other types of fires. Final thing here, we're going to bust some fire myths, right? So the first myth is that small fires are totally predictable and aren't dangerous, right? So the prediction game doesn't lead to any good place. We don't want to be predicting, right? If you put, smoke detectors in your house, it's not because you made a prediction that there was going to be a fire, 300 days from now. It is not predictive. In fact, it's better to kind of admit ignorance. You say, I don't know. There could be a fire at any time. Let's just focus on the outcomes, not the probabilities. And that is called being smart, because survival is important, right? Most fires happen from sunlight or high outside temperatures. Our second one, right? This is not true, right? So vast majority of fires are going to be started by people. In the context of wildfire or fire that spreads out of control, tends to be unintentionally started by people, but the vast majority of all fires everywhere are intentional, right? Started by human beings for their own purposes, though these can accidentally get out of control, and this is where most of our fire hazards later on are going to come from. The flames and heat are the most dangerous part of any fire. This is not true. What is a dangerous part? Is the smoke, right? Tends to be extremely severe, depending on what is burning, can poison the people, make them sick, incapacitate them extremely quickly. Smoke can travel long distances. The smoke can have products in it, things like carbon monoxide, which are not easily detectable by human beings, but can still incapacitate them and lead to all these other bad effects. It is actually the smoke, not the fire, that tends to be worse, broadly speaking. And then all fires are the same and can be treated the same way. So we just kind of talked about why that's not true. And we'll talk about how big, extreme, really, really intense fires tend to be really bad for the environment, but small fires, regular fires, kind of fires that normally happen whenever nobody intervenes, those are good. And that's going to lead to our section on fire and ecology coming next.